Thanks for the introduction, and thanks to the organizers for the occasion, for the opportunity to speak here. Yeah, this is the title of the talk, and I'm stepping a little bit back from the tropical world for a minute. And I start with a problem that I'm sure everybody in the room is very well familiar with, the convex hull problem. And I'm going to talk a little bit about software. I'm going to talk about some experiments which were done with a computer, and some algorithm addressing this problem. And for the end, I will talk on something completely different. But if I'm lucky, so the talk might end up in a full circle. So we'll see. The convex hull problem, as you know, is as follows. You have a couple of points, and you want to compute the convex hull, and this might look like this. I should be a little bit more precise here, because I didn't really specify what I meant by that. If I want to be precise, I would prefer the convex hull to be specified by the normal vectors of the facets of the convex hull. So there are other ways, for instance, in terms of triangulations or in terms of the face letters of the polytope and so on, but this is the thing that I would prefer. And as you also know, this is, has a dual formulation. Given a finite set of affine half spaces, compute the vertices, provided that it's bounded. So for the purpose of this talk, all the polyhedra will be bounded. And as you also know, this is not much of a restriction. And by means of cone polarity and an LP-type oracle, which finds an interior point in a set of, in the intersection of half spaces, this is actually equivalent. So what do we know about the convex hull problem? Well, quite a lot, because this has been studied, as you also know, for several decades. But still, I want to give you a basic idea of what the algorithms that we know as of now look alike. Well, the algorithms, there are very, very many algorithms, but in a way, they can be categorized in rather small number of categories. And the first big category is those of incremental convex hull algorithms. So what's the idea here? Well, we just start with some set of points that we know the convex hull of. And so say all the points span the space that we are considering. So then if you have d plus 1 points in d space, and let's hope that it's in general position, then they span a full dimensional simplex. And then we can add points and further update our information on the convex hull to finally end up with a convex hull of all the points. And this is what we are after. But so the nature of those incremental convex hull algorithms is such like they have to compute the facet descriptions of all the intermediate polytopes, and the running time behavior very much depends on the insertion order. So, and there are two subfamilies, I should rather say, or two algorithms. So one of them is the beneath and beyond method, which starts out with this one simplex and adds further vertices to the convex hull, and in order to do so, maintains the triangulation of the intermediate polytopes, and also in particular of the final polytope that we produced. And as you know, some polytopes may have large triangulations, and this could possibly lead to problems in terms of time. We'll come to that later. Of course, this is not the only idea that came up for dealing with the convex hull algorithms. A different idea would be like gift wrapping. I'm less precise. So this picture down there pretty much refers to a beneath and beyond type computation, where you already had the convex hull of these yellow guys over here. And if you add this 1 point more, then you have a notion of violated facets that have to be thrown away from the list of current facets, and while those two are kept, and so new are added, and so on. And the gift wrapping has a different strategy. So you have a, so you just try to find the points, the facets one after another, just in along a path in the dual graph of the polytope. And again, there are several variations, and one of them being the reverse search method by Avis and Fukuda, which is strongly related to the behavior of the simplex algorithm. But I'm not going into those details again. And there are many more algorithms, and there is one more idea that I want to mention, and this is divide and conquer, which is very familiar to be a very, very good idea for very many problems in computer science. But for convex Hull algorithms, it turns out this is only useful for small dimensions. And the reason being that the combinatorics of high-dimensional polytopes can be surprisingly weird, maybe. So this is just one way of phrasing that. But for small dimensions, in particular dimensions 2 and 3, this is a very good idea. Just subdivide your set of points in certain ways, compute their convex hulls, and combine. And if you want to learn more about algorithms on convex hulls, well, there is the survey paper by Raimund Seidel, and in the Handbook of Discrete and Computational Geometry, edited by Eli Goodman and Joseph O'Rourke, and the second edition will appear by next year, I suppose. Let me sum up some of the theoretical results. Well, as I said, so there is really a large body of work that had been done, and I'm just mentioning a few papers, and my apologies to all those in the audience that I forgot here, but there are just a couple of things that I want to point out. So if we were interested in the complexity of the convex Hull problem, then there are various distinctions to be made. Firstly, so I have to exactly specify how my input looks like. I have to exactly specify of how I expect the output should look like. And also, I can fiddle around a little bit with the parameters. So one thing that had been studied is, suppose the dimension is fixed. So this is probably because people experience, well, low-dimensional convex Hull dimensions are already quite interesting. And so it makes sense to consider the convex Hull problem for small fixed dimensions. And there has been a lot of work, most notably the landmark paper by Clarkson and Shaw, which gave a randomized algorithm with that complexity given there to solve that problem. And you can see there's a difference between dimension 3 and the higher dimensions in terms of the explicit form the complexity has here. And I can combine those two, as I did in the next line, because the capital O notation takes care of all the rest. This is exactly the same complexity that Chazelle produced by giving a deterministic algorithm and by applying de-randomization. I have to say, the Chazelle algorithm and also the Clarkson-Shaw with the same complexity are asymptotically optimal. I'm just talking about worst-case complexity here. And I'll come back to that in a minute. For small dimensions, there are various papers which appeared for various small dimensions up to 5, as far as I know. And in particular, there's a paper of Chan, which gives an optimal of n log h deterministic algorithm for small dimensions. I didn't tell you what the h is. This is the number. So this is the output size. So this is an output-sensitive algorithm. So let's forget about dimension 3. In dimension 2, it just says, so this is just the number of vertices on the convex Hull. And this is, one can show worst case optimal. Okay. So half of the slide is still left for something else. What is this? Well, we could also consider the case that D is in fact a variable, so part of the input. And, but then, wait a minute. So, well, the world of theoretical computer science or complexity theory is probably to a large extent about fast algorithms, and fast often meaning polynomial time algorithms. And if you just consider the input size for variable dimension, then there's no hope that you can ever end up with a polynomial time algorithm. Why? Well, if you just take the points of a regular octahedron, which is 2 times d in dimension d, and want to compute their convex Hull, the number of facets is 2 to the d, due to the vertices of the cube in the same dimension, and this is exponential. So for variable d, there's no hope for a polynomial time algorithm in a naive sense, but Well, maybe we should take into account the size of the output. And this is what is usually done. And if you want to do it like that, then Avis and Fukuda came up with a very clever method. I already mentioned this reverse search method, which is polynomial and with a low degree of order m and d, provided that the polytopes are of a very easy structure in a way. So they are simplicial, meaning that all the faces are simplices of the respective dimension. For instance, if you have points in general positions, then this will apply. But this algorithm and all the other known algorithms that I presented previously are known to be worst-case exponential. And the general problem, whether or not there exists a polynomial time algorithm in this sense, so output size taken into account, is wide open as far as I know. And no surprises in this talk, so I say that right now. So it will even be open after the end of this talk. Backing up for that slide again. Why these funny numbers here, these exponent n to the d half, rounded down? Well, you already know that. So we have the cyclic polytopes, and so this is their asymptotic number of facets that they have. For instance, if you take the points on the moment curve, this is an example in R2-3, and compute their convex hull, then you have those many facets, and McMillan's upper bound theorem says, well, this is as bad as it gets. It is important to know that these are by no means the only polytopes which attain this bound. So this property, so all the neighborly polytopes attain this bound, and there are quite a few. But this is, again, something that I don't want to go into. But what is important to understand to interpret the results for the asymptotically optimal results for fixed dimension is that the reason why they are asymptotically optimal is, to cut a long story short, because these guys exist. They are responsible for that. But there are very, very many other polytopes. Maybe you are not interested in cyclic polytopes, and why should you suffer in terms of your algorithm complexity just because those exist, right? Okay. Since computing convex hulls is quite important because it has so many applications, and you heard about a couple of those in previous talks and also in the previous workshop on computational geometry, there have been very, very many implementations. And let me just point out a few of them. So David Avis implemented this reverse search method, and there's this one of the most used programs for convex hull computation is probably the Q-hull. And of course, there's this very big project on computational geometry called Seagull, and also they have convex hull codes, various kinds of low dimensions, and in particular one which works in arbitrary dimensions. And then there's Ken Clarkson's famous hull program, which is, I think, Nina's favorite as far as I know. And then there is CHD by Yanis Emiris, and CDD by Kome Fukuda, and his most recent versions just appear as libraries. So this is the most recent one. And in the Polymake project, we also have an implementation of the beneath and beyond method. So the algorithms of all the programs so LRS is gift wrapping. So this is gift wrapping, incremental, 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 incremental. So this is incremental Fourier-Motzkin, and these are various variations of beneath and beyond and some variations. And this is, again, incremental beneath and beyond. I want to go a little bit further about what we know about the theory of convex hull computations. But before I do so, I would like to show you a couple of computer experiments. And we did the computer experiments with the following programs, so the four that just survived after what I did before. I know Ken Clarkson hates me doing that. But for the convex hull problem, if you want to really specify it, you really have to say exactly what you mean. So, and I stand by what I said on the first slide. I want to have the normal vectors of all the facets that the convex hull has. No exceptions, no excuses, no rounding off, no errors. And for that, it is known that exact arithmetic is essential, at least for dimensions above 4. So up to dimension 3, you can do some tweaking to get around that. But up to dimension 4, you really have to play according to the rules of the game. And there are various ways to deal with exact arithmetic, as you know. And the easiest way is just to restrict to rational arithmetic, although this is known not to be a very clever idea in some circumstances. Sometimes it's clever to have something like floating point filters as implemented in the Leda reals or in the core library by GUp. Well, we didn't use this advanced methods for arithmetic because for several technical reasons. But we wanted to get an idea of the behavior of the codes and of the algorithms. And in order to do so, it was essential just to restrict to one kind of arithmetic for all of them. And the easiest is just to take the GNU rational arithmetic. So everything you will see in a minute will use this arithmetic. But before that, let me just make a very short commercial break. During that, you can take a small breath until I bury you with numbers from computations. No, it won't be that bad. But so this is a joint project with Evgeny Gavrilov, going on for some time now. But there are contributions by 2 students of mine, Thilo Schröder and Nico Witte, quite a few. And also some other people, including Volker Keibel and Julian Pfeifle, who contributed some pieces to the code. And initially, this project was just about algorithmic approaches to convex polytopes, and in particular, convex hull computations, but many other things, in particular, constructions of maybe strange polytopes. For instance, one of the recent constructions by Günter Ziegler and Alex Schwarz is for a cubical 4 polytope with an odd number of facets, where this also played a role. Sometimes it's interesting to visualize polytopes, and all this is what you can do with Polymake. But since last summer, there's more. So we went topology-wise, and so we can compute simplicial homology. We got a couple of more advanced stuff as well. For instance, one application, you can use this application in order to recognize the certain types of topological types of certain 4 manifolds just from a triangulation. This is what we used it for. And other things like constructions of 3 manifolds in the combinatorial setting that I talked about here in this audience a couple of weeks ago. And, well, there's no end to it. You can, if you think there's something missing, so don't always send an email to me, but you can do it yourself. This is the message. It is really extendable in various ways. And if you're interested in that, look at our webpage. It is free code. You can download. It's open source. You can read through all the thousands lines of C++ code if you want to. And of course, I'm also open for questions later and a short demo if you want to. For the tests, so these are the rules of the game that we made. I'm not going through that. But let me just point out there is a very interesting survey on computational results by Avis, Bremner, and Seidel, now quite a couple of years old, which showed very, very many interesting facts about convex hull algorithms and really improved our knowledge on the subject considerably. And these results are meant to tie in with their results. So we really made an effort to make our results comparable to the results of those. Okay. So this is the first of the results. So these are the 4 programs that qualified. And so this is Seagull, this is CDD, LRS, and this is Beneath and Beyond. And
what are you doing here? I didn't really understand what the previous slide was saying. Comparing some programs?
Yeah, I'm comparing programs, and this was the setup of the test. So we used a machine of this type with that much memory, and we restricted the computation like that. I didn't want to go to the details. I said it was just made in a way that is probably sensible. So, And this is the data which came out. So this is just the input size on all the slides that you will see. This is the computer, the CPU time used in seconds, and it's a logarithmic scale. And this input size will vary from slide to slide. And this is for this time. These are all random polytopes existing in dimension 6. It just happens to be 6 for this slide. And the points were uniformly sampled from the unit sphere in dimension 6. And to some precision, and you get awful denominators if you round them to exact rational numbers and then compute with these numbers exactly. And for all those computations, so they spend 99% of the time, regardless of the algorithm, in the arithmetic, no matter how clever your data structures are. So for these examples, arithmetic seriously matters. So this is how you can think of it. So this is a sequence of spheres. So for lower parameters, it looks less than a ball, and for higher parameters, it looks more like a ball. And this is what it looks like. And so those of you who attended the previous workshop on computational geometry saw that also various convex Hull computations, and usually those guys have some diagrams which end not at 500, but somewhere in the order of 500,000 maybe. We can't do that with this exact arithmetic, but I just decided to stick with this just to make it comparable for those algorithms. You could use, for those things in particular, faster arithmetic for all the algorithms in principle, and this would be just amount essentially to a scaling of the curves. So that's why it is, for the purpose of my talk, it is not important whether this ends up at 500 or 500,000. But what is important, it's also not important which program is going to win, but it is important, so how do the curves look like? What's the shape of the curves? And so the behavior is benign, more or less, right? So it's a logarithmic scale, but it's not so bad. So we can compute convex hulls of a fair size for those kinds of examples. This is what the slide says. And essentially, all the algorithms do fine, roughly speaking. So
is this O of n to the 3 as our expected constant dimension equals 6?
yes. So for the beneath and beyond type method, yes. If the algorithms actually match that, yes. But it is, they do. So both of them do. This is a different something. So as I said before, so sometimes certain geometric properties are responsible for the fact that convex Hull computations are complicated. For instance, sizes of triangulations matter, or might matter, depending on the method. And as you know, for instance, products of simplices have rather many simplices in each triangulation. All of them have the same size. And if you're now leaving the realm of fixed dimension, and instead now the dimension is growing, and you're looking at products of simplices of equal dimension, so like that, so the smallest would be a square, product of two 1 simplices, product of two 2 simplices, product of two 3 simplices. Then when you run the algorithms, then only one of them does pretty good, and all the others, so the curves just stop here because for that one, because we decided we don't want to wait longer than 1 hour for the output, and those two producing the triangulations just die because we didn't give them more than 400 megabytes of memory. Right? So they just die because they can't store the triangulation any longer. But in this case, the double description method, or Fourier-Motzkin, can do pretty well. So this is another. So we have a class of polytopes where we can, if the input is random, so then more or less all the algorithms do fine. So this was the message of the first picture. So now the next slide says, well, there are other classes of polytopes for which some of the algorithms do fine. But, you know, this is not the end of the story. And before I show you the third computation, let me do a little bit of geometry here. So this is a construction that I find, this is not due to me, it's due to Avis, Bremner, and Seidel. And this is really, for some of the problems, key, which tells you why convex Hull computation is so complicated. Well, what do I want to do? I start out with a standard cube, say 0, 1 cube in the dimension d, which looks like this. So we had this before, so it has 2 to the d vertices and 2 times d facets. And then I consider a certain half space, this, and this separates the cube. And if I take this as an additional inequality, then my 3 polytope in this case looks like this. And this is called the dwarfed cube. So what do we know about it? Well, like the cube, it is a simple polytope, meaning in dimension d it has exactly d edges passing through each vertex. So this is the notion dual to simplicity. And it has 2 times d plus 1 facets. Well, all the facets of the original cube survived, but we added 1 more, so this is 2 d plus 1. And, but most of the vertices are killed. So only d squared plus 1 survive. And if you're familiar with the lower bound theorem, then this says for this number of facets, and for a simple polytope, this is the absolute minimum of the number of vertices which is possible, meaning this polytope is dual to a stacked polytope. So in a sense, this polytope is, in the combinatorial way, as people would usually perceive it, is as simple as it gets. But the coordinates are a little bit weird because of this way that I produced this thing. So what is interesting about the dwarfed cubes? Well, look. No, so this is 3 rotations of the same guy, that you get the idea. So in general, so these, what are these d squared plus 1 vertices? So this is the origin and all its neighbors. And so these are the original vertices, and the new vertices from the cutting. For each of those that survive here, you get d more neighbors. And this totals to d squared plus 1. Okay, and this is the problem here. So it's a small polytope. So for this computation, the facets are the input. And in dimension d, so this is just dimension, I don't know, 18 or something. So it's a small polytope with 2 times d plus 1 facets. And the convex Hull computation looks pretty bad. Well, so we have polytopes for which none of the known algorithms does good. So we have various optimal convex Hull algorithms, but we don't have a good one. Okay. And this is now another theoretical result which just gives an explanation of what was going on here, and this is way more general than just talking about this one specific one-parameter family of polytopes, and this is due to David Bremner. And this is about dwarf products of polygons, and which goes as follows. So instead of a cube, you take delta copies of an esgon. So this ends up with because this is a 2-dimensional polytope, the total dimension of the resulting polytope is 2 times delta, and it has still this parameter s, which was the esgon here. And we have very, very special coordinates. I don't tell you what these coordinates are right now. And again, like in the case before, we add 1 more facet, which does all the crime. And we end up with a polytope which has this number of vertices and this many facets. And again, it is dual to a stacked polytope. And because what's the number of vertices of the real product of polygons before the dwarfing? Well, so if I take the products, so the number of facets add up, and the number of vertices multiply. So that is to say, since I have delta copies, I have s to the delta vertices and delta times s facets. And again, only very, very few of those vertices survive. And if I now have an incremental algorithm which wants to compute those vertices, and I happen to make the mistake that I take this dwarfing facet as the last one, so then I cannot get a polynomial time algorithm, no matter how it works, as long as it is incremental, then it will have this super polynomial running time. So now you say, well, but this is extremely stupid. So, of course, why don't you use randomization? Well, because randomization just gives you an additional factor of d plus 1. So it doesn't gain you that much in this case. It gives you a little bit, but randomization doesn't help. So you still have intermediate sizes of polytopes of that order. And this is the reason, well, this is just one construction. And, but if you're really working with polytopes on a combinatorial level of higher dimensions, so then you will see very often polytopes which are really, really complicated and not random at all. And so really this high-dimensional convex hull problem is sometimes a problem. But as David Bremner showed us, incremental algorithms are a bad idea. So what do we do then? Well, there's one way we could do it differently. And we could think about a reformulation of our original problem. So it is known since the 70s that the convex hull problem is in fact equivalent to a decision problem up to polynomial time transformations. And what's the polytope verification problem? This is this decision problem. I have a set of points, and I have a set of affine half spaces, so both in R to the D, say. And then I have the interior, so the convex hull of the points and the intersection of the half spaces. And the decision problem just asks, do both coincide, yes or no? That's the decision problem. And so, again, just this image. And I don't know, maybe someone in the audience knows, it might be due to LOVAS. This was somebody gave me that hint, but I don't know. So at least, so this is a folklore result now, by now. And I don't know whom to attribute it to. And the interesting thing is that it is polynomial time equivalent to the convex hull problem. I'm not going to give you the full proof, but the idea is that, so starting out with so say you have, you want to compute the vertices of a polytope given as an intersection of half spaces. So, and you compute the vertices one by one. And so you start out with the empty set, and after a couple of sets, you have a couple of vertices. Well, and now you want to compute a new one. And you just do it by just specifying, so setting some of the hyperplanes to be 0. And by recursing over the dimension, you will eventually find a new vertex, unless you were already done. So this is the short story of that one. And the reason why this is interesting is that we can go a little bit further with the reduction, and this is this problem. So let's think of P and Q, two polytopes which just arise as in an instance of the polytope verification problem that we had before. And so they can be completely unrelated. And I want to normalize the situation a little bit, and this is how it works. So if I want to decide whether P and Q are the same, then I first check the dimension. Well, this is easy for this guy. I can do just Gauss elimination. But for this guy, as you know, this requires an LP-type oracle, while finding an interior point in this description is equivalent to solving an LP, again, up to polynomial transformation. And of course, if some of the half spaces just tries to cut off one of the supposed to be vertices, there's no hope that both of those descriptions coincide, and I check for that. And if still the candidates P and Q survive for my test, then I remove all the hyperplanes which have the property that the intersection with the polytope has the wrong dimension. So if those are facets, so then the set of points which intersects has to be of dimension exactly d minus 1. And again, I can check this by Gauss elimination. And I kind of have the dual operation to remove non-vertex points. Well, there's a red star. I don't know if you can see it in the back. So if I threw away, this is not the complete list of facets, so then in this process, I might throw a couple of meant to be vertices, which just die in this process, but that's not a problem. And I end up with a polytope completeness problem. So what's the input? I have one polytope, and I have some of the vertices and some of the facets. And the question is there anything missing? And this is, so are any facets or vertices missing? And one can prove if vertices are missing, then also some, if I do it in this order, then some of the vertex facets must also be missing. And again, it's just a decision problem. Output is just yes or no. And I like to call such a guy here a partial polytope. And so seeing it as a polytopal complex, it's like that. As its vertices, it has those input vertices. And what are the maximal elements of the poset of the polytopal complex? Well, these are the intersections. So is the convex hull of the vertices contained in each of the facets that I see. So, and if we put all those together, then we get a polytopal complex like this one. And this is what I would like to call a partial polytope. We'll see an example in a minute. And then if you think a little bit, you come up with this result rather quickly. If you now apply standard methods from simplicial or polytopal homology, then the d-1 Betti number must be 1 if and only if this description is complete. So I will come to a short proof of that in a minute. So it is certainly, if it is complete, so then the polytopal complex that I described to you is just the boundary complex of a polytope, which is a d-1 dimensional sphere. And this happens to be the Betti number of the sphere in dimension d-1. For the converse direction, I will give you an argument in a minute. Let me point out, this is true for an arbitrary field, right? Because the sphere always has Betti number 1 in top dimension, regardless of the field. I could even use a weird ring, but this is not essential. So let's stick to fields. And this is what it could look like. So this could be a partial cube. So it has the lower facet missing, it has the upper facet missing, and it is this one vertex missing. And because this vertex is missing, also this facet that I actually see is split into half, but this is how it looks like. And in this case, it is homotopy equivalent to a circle, and that's why the Betti numbers, if it's not reduced, so it is 1 because it's connected, and because it's a circle, it has 1 in one dimension. But in the dimension d-1, it is 0, right? So, so how do I prove now the other direction of this statement? Well, so a partial polytope is an induced subcomplex of a polytope. This is the idea. Of course, this is wrong, because you see the counterexample here, right? So this triangle, because we have triangular facets here, these are just not faces of the full cube. But, well, it's almost true. If I triangulate in the order that I take the vertices first that I have, for instance, by a beneath and beyond type algorithm that I showed you previously, and add the missing ones later, then I get a triangulation of the thing as an induced subcomplex, and then it immediately follows so that this is true. Okay, but the problem is I don't have this input. I don't get at this from the data that I gave you, just the points and the facets. How could I compute this partial polytope? Well, without doing a convex hull computation on the facets. So this would, again, be a recursion step over dimension, but I want to avoid that. So, and what I'm telling you is that this is not necessary. So this is the combinatorial picture. How is this to be interpreted? Well, so this is a matrix, 0-1 matrix if you want to, and where nothing is written, it is 0, and where a star is located, there's a 1. And what are the row numbers? Well, these are just the facets that I see. And these are the vertices that I see, and I just have an asterisk wherever I have incidence. So if you have the incidence matrix of a polytope, so then this is just some minor of for some set of rows and some set of columns of that incidence matrix. So this is this input, and the message is this is enough to compute this Betti number. Why is this? Well, first, the intuition, rather than working with these quadrilaterals, which cause all the trouble, I can conceive them as blown up in higher dimensions such that they are simplices without changing the homotopy type. And this is the more elaborate technique, is calling this thing the crosscut complex. And this is known to be homotopy equivalent to the boundary complex of this partial polytope. Well, more formally, I take this crosscut complex is just a simplicial complex with the vertices that are given, just the columns of this matrix here. And as the facets of this, or faces of this simplicial complex, I take everything which is generated just by the rows. This is exactly the crosscut complex in this case, and Rota proved that it's not so terribly difficult to prove, but it's utterly useful that it is homotopy equivalent to the partial polytope that I started with. Pardon? Well, this is just the intuition behind. So just to give if you, of course, this has no straight line embedding as a full dimensional simplex and as the same time as this partial polytope in R3, but this is just the intuition behind. Is this question answered? Or? Okay. So, and now we have an easy algorithm to compute a solution for our convex hull problem, for the polytope completeness problem, but via this, also for the convex hull problem. So I have a minor for often some incidence matrix, and I also have the dimension. This is, of course, essential because I could have a partial polytope. If I don't have the dimension, there's nothing much to hope for. For instance, if I have the cube and just the top and the bottom missing, so then this is homotopy equivalent to a circle again, and then this is at the same time an incomplete minor of the incidence matrix of the cube, but at the same time a complete, so the whole incidence matrix of the quadrangle. So if I don't have the dimension information, there's not much to do. But if I have that, I can compute of this possibly high-dimensional simplicial complex. So the dimension of the complex is just the maximum number of vertices on one of the facets that I see minus 1. And I have to descend maybe to compute the boundary matrices of dimensions d minus 2 and d minus 1. And then I just compute beta d minus 1 as the difference of co-rank and rank respectively. And remember, I still have one free parameter, which was the field, and I choose the easiest field that I could possibly use. If you don't like it, you can also do it in characteristic 3, of course. And yeah, and I return yes if this Betti number is 1, and the only other option is that it is 0. And this is joint work with Günter Ziegler. Okay, so what have we got? Well, if our polytope is simplicial, then we get an O to the m to the 4 algorithm, which is not so bad because it's, after all, it's a polynomial time algorithm. But it's, of course, worse than this m times n times d of Avis and Fukuda. So we didn't gain much there. But at least we ended up with a simplicial algorithm, with a polynomial time algorithm in the simplicial case. Another thing is, so remember, for the matrix that I showed you, I didn't specify which were the rows and which were the facets and which were the vertices. In this formulation, it's completely symmetric. So we can choose, actually, whichever gives the smaller dimension to cut down a little bit on the running time. And in particular, this proves that the polytope completeness problem is, in a sense, complexity-wise, self-dual. So if you have a class of polytopes which has a polynomial time polytope completeness problem, then the dual class has the same property. And this has previously been investigated by Bremner, Fukuda, and etc. But again, because, as I said, the dimension of the crosscut complex can be really big, this won't give us a polynomial time algorithm in the worst case. Very easy to come up with examples. But so suppose you could compute the Betti numbers anyway better than I just suggested, maybe in polynomial time, then this would give you a polynomial time algorithm for the convex hull problem. So the bad message here is that the complexity status of this problem is open as well. And so this algorithm is only of theoretical interest. But it just, so the punchline here is, it just bridges it connects two problems. So the convex hull problem is, in fact, weaker than the problem computing the Betti numbers of a high-dimensional complex. Just one Betti number over GF2. So this is the message. I have no idea. So, other than what I just told you before, but, so, sorry, was it? No, it's not. I'm not saying that it is of the same complexity. I'm saying if I could compute Betti numbers quickly, then I can solve the convex hull problems quickly. In that sense, I think, and yeah. So it is. I think it's strictly more complicated than computing convex hulls. This is what I suspect, but I cannot prove that either, because, as I said, as far as I know, it is unknown whether or not there exists a polynomial time algorithm which just computes the dth Betti number of a k-dimensional complex over GF2, or just decides whether it's one or not. So this is the only thing that I need. So it is. So this is what I'm just saying. So of course, if you do it via boundary matrices and computing ranks, then you're doomed. So there's no way. But maybe you have something more ingenious to come up with, then you could end up with a fast convex hull algorithm. So this is all I'm saying. Okay. So this is what I wanted to tell you about the convex hull problem. And you might have wondered why this talk ended up in the section on tropical geometry. Well, and most of you will have figured it out by now. But so now we are going tropical. Just let me review one of the whirlwind slides of Mike DeValent from his last talk. So we are now considering the tropical semi-ring, with this tropical addition being the minimum and the multiplication just being ordinary addition as before, and the tropical projective space, which makes sense in the, if you're just considering tropically convex sets in R to the d plus 1, because they are closed under taking tropical products, tropical scalar products, and that's why we factor that out. And Mike and Bernd defined the tropical convex hull of points, of endpoints in this space. Yeah, well, actually they define it differently, but it turns out to be equivalent, as the formal set of linear combinations of those points with arbitrary real numbers. But since we factor out this one dimension, it'll be compact. So, and well, and these are examples of polytopes in dimension 2. So this is a triangle. This is also a triangle. It's a little bit skinny, but there's nothing wrong with it. And this is a 9-gon, and there are weirder guys. So what I want to do for the remaining 10 minutes is to study the convex hull problem for tropical polytopes in a way. But wait, what's the convex hull problem for tropical polytopes? Well, Mike didn't mention, so it should be the computation of the facet normal vectors, but what's the facet normal vector of a tropical polytope? Mike didn't tell you, and because this is probably not well defined what it should be. But so we have to work a little bit until we make it into a reasonable problem, right? So no facet normal vectors up to now. And this is what the next two slides are about. So again, this is what you saw previously. If you have a tropical linear form in D plus 1, then the set of points in the tropical D space, which have the property that the tropical scalar product vanishes, and vanishing meaning this minimum is attained twice, and the reason why this is a useful definition you also saw in Mike's talk, then this is the definition of a tropical hyperplane. And this has been studied by Bernd Sturmfels and various co-authors in various papers in the last few months. And this is another picture that you already saw. This is a tropical hyperplane in the tropical projective plane. Okay, so far, nothing new. But so we would like to, so what's so different about the tropical hyperplane other than the ordinary hyperplane in the plane, affine hyperplane, meaning a normal affine line? Well, an affine line separates the space into two halves, one of them being positive, the other being negative. And if you recall everything you know about the convex hull codes that I didn't tell you in the talk up to now, well, then this positive and negative half-space distinction plays a role in all those algorithms. And if I want to end up with a convex hull algorithm, I should better do something about that. Because if we look at this in dimension 2, it separates, so the complement of the hyperplane just has 3 connected components. And if I go to higher dimensions, it gets even worse because it has d+1 connected components. But okay, bear with me, everything will be fine. But so those guys will be important, and they are called open sectors. And what if we just glue together a couple of them? And this is my suggestion as a definition for a closed tropical half-space. I take the non-trivial union of closed sectors. Closed sectors, so we have the usual topology. So this pink sector plus this black 2 lines. Of course, this extends to infinity in 2 directions. This is a closed sector. This is another closed sector. And their union is just this part. Non-trivial just meaning, well, I have to take at least one, but I am not allowed to take all of them. So, and then it will give me a separation of the space into 2 halves. And, well, it doesn't look so bad. A little bit weird, a little bit skew, but, well, it looks a little bit much more like a half space than one of those sectors alone. Okay. So what are we going to do with it? Well, so if we now have a tropical polytope, then what should be its faces? Well, not the things that you see at first sight if you look at a polytope. Tropical polytope, it will be something a little bit different. Let me define a prefacet, which will be an intersection of a tropical polytope with a minimal closed tropical half space. So the tropical half spaces that contain a given polytope are partially ordered by inclusion, and I just take one of those minimal guys. And because there is something like a tropical separation theorem, very easy to prove, and I gave a proof of that previously in a previous talk, so you can see, well, the polytope will be defined by all those minimal half spaces, but still we don't know how many do we have and how do they look like. Well, I'll tell you. But before that, so we also want to have, so these are the prefacets, and if I have a set of prefacets, I want to define what is the face in their intersection or something similar. Well, I take the intersection of the sets in the tropical D space, but intersect that with their set of vertices. Vertices are something which exists for tropical polytopes, and take their tropical convex hull. Looks a little bit complicated if you're used to polytope theory in the classical world. Well, you don't have to do this part in the ordinary world, but it turns out that it is necessary to do so here. And this will be a face. And one can prove that the faces, again, form a finite distributive lattice, like you would like to have. And I'm not going to the proof of that, but I will show you a picture. Well, so this is a perfectly normal tropical quadrangle. And what are these prefacets? Well, I give you 4. So if it is a quadrangle, then it should have something like 4 facets. Well, and so here are 4 tropical half spaces. For instance, the white one is just, so this is just one sector containing this yellow tropical polytope. So this is one half space, tropical half space containing the polytope. So everything below the dark blue line, so this is the union of 2 sectors containing the polytope, is a tropical half space. Everything left or below the brown line is a tropical half space, again, the union of 2 sectors. And the purple one is, again, the union of 2 closed half spaces. But if you look at it carefully, the intersection of those 4 half spaces is not the tropical polytope. Why? Well, this point out here. So all the points here are still in the intersection of all those 4 half spaces. And for those prefacets, it turns out that my quadrangle has 2 more prefacets, being those vertices. So you have to add those 2 tropical half spaces in order to get an exterior description of this tropical polytope. But other than that, there's nothing wrong with it. What is the exact question? Pardon? Well, I just take the minimal half spaces. So if I have a half space, for instance, which would.
No, and I think he has his polytope is the convex hull of those 4 black.
Yes, the polytope is defined as the convex hull of the 4 given points. I start out as the tropical convex hull of 4 points, and then and then I have 6 half spaces in this particular case. So this will be at least 4. I have at least 4 half facets, prefacets, and at most 7. But again, this is nothing which is important right now.
Could you say once again so the prefacet is intersection?
Yes. So the prefacet corresponding to the white half space is just this tropical line segment, and the blue is this one. The brown.
I mean, just the definition, because what is written there is kind of strange, but probably will mean something a bit different.
So, what is wrong?
If you intersect P with the half space.
Oh, sorry. With a boundary. Sorry. Of course, this is wrong what I just wrote here. This is intersection with a boundary of a minimal closed half space.
Boundary
In the usual sense, yes. Thanks for the question. Yeah, this is a mistake. So the one prefacet is this thing, one prefacet is this thing, one prefacet is this thing, but they don't form a clutter, so all of them, because these 2 guys being contained in the line segments also are prefacets, although they are not maximal elements in the lattice. And I would like to call those facets which are just maximal. Okay. And we have more gadgets on the tropical world, in particular the tropical determinant. And so as you know from the ordinary world of convex polytopes, you have these wonderful affine half spaces, and you have algebraic descriptions in terms of signs of determinants, and we want to do something similar in the tropical world. Well, this is just the formulation of the tropical determinant that you saw in the previous talk. And so this is a minimum now of a couple of expressions which are just indexed by elements in the symmetric group on d+1 elements. And this whole thing is singular, tropically singular, if and only if this minimum expression, so this is a minimum over d+1 factorial expressions, is attained at least twice. And this is equivalent to saying that the row or column vectors are contained in a tropical hyperplane, and this has been studied by Richter, Ebert, Sturmfels, and Theobald. Okay. But now we define a sign. How do we do it? Well, if this is regular, so then this minimum is attained for exactly 1 permutation. And there are odd and even permutations. Why don't take their sign and 0 otherwise? And it turns out this is the proper thing to do. If we take d fixed points and consider the map that maps all the points in the tropical d space just to the tropical this is wrong, sorry. To the tropical sign, this is what I wanted to say. So to the tropical sign of the matrix with columns x, p1 to pd, then the inverse image, unless the whole thing is trivial, the inverse image of 0 and 1 is a closed tropical half space, and each closed tropical half space arises in this way. This is a theorem. Okay, now we are done, almost, right? So now we can define the tropical convex hull problem, blah, blah, blah. I spare that, but we have algorithms. So at least in the 2-dimensional tropical world, the high-dimensional tropical world in terms of convex hull algorithms is work in progress. But in the 2-dimensional setting, we have exactly the same bounds that you know from the classical 2-dimensional convex hull algorithms. We have a worst case optimal n log n algorithm. And to prove that is almost the same as in the ordinary case, because we could give various algorithms, for instance, something based on sorting. You know that the ordinary convex hull problem in dimension 2 is very closely related to sorting. And again, you can do a sorting trick here to produce such an algorithm. Well, then you can, in order to work with random input, you can sort in a clever way, and this will give you the same bounds as in the classical case by bucket sorting. But you can also use Jarvis March with chance trick of overlapping polygons to get an optimal O of n log h algorithm, where h is just the number of vertices of the tropical polytope. And this is what I wanted to say. Thanks.